Empowered minds, rise and soar. Use your own AI, we'll explore. Help the future hand in hand in this tech-driven wonderland.
Okay, hello everyone. It's the new episode of Office Hours. Today we have Rand from Zama. Is it how you say it, Zama?
Zama, yes.
Zama,
Hey,
yeah.
everyone.
Yeah, Rand, do you want to say a couple words about yourself and the company?
Sure, of course. My name is Rand. I'm the CEO of Zama. I've been a developer since I was a kid, built my first company in the 90s as a teenager. Then I got into AI back in 2003, did a PhD in machine learning in 2007 when I was 21. And then I ended up building one of the first privacy-preserving machine learning company that I sold in 2019. And since 2020, I've been building Zama with my co-founder Pascal Payet, working on a technology called Fully Homomorphic Encryption, FHE. The idea of FHE is that you can compute on encrypted data without actually having to see it. So, today on a blockchain, all of the data on chain is public, right? So anybody can see how much tokens you own, or how much you've been transferring, and things like that. With FHE, you can actually keep this on-chain data encrypted, but you can still actually run smart contracts on them. You can still keep it composable. So you can add a layer of confidentiality on top of existing smart contract blockchains. So this is really what we're excited about Zama and we're currently doing.
Awesome. So when I think of homomorphic encryption, the analogy in my head, even though they somewhat unrelated, is zero-knowledge circuits. Because the way I understand it is that in both cases you have some arbitrary computation that you need to convert it into some other form on top of which you can do do some cryptography magic, right? Is it like a meaningful analogy, or is it like how would you explain homomorphic encryption very briefly to people who want to understand it?
So try to imagine that I don't know. Imagine you have a secret recipe for like a great pizza, right? But you don't have an oven, so you cannot cook the pizza. You just have the ingredients. FHE is as if you would basically put your ingredients in an oven, close it, so nobody knows what ingredients are on the pizza, but then someone else comes in, presses the buttons, basically cooks the pizza, and then you take it out and you basically get like the cooked pizza, right? So the person who's actually operating the service, in this case the oven, doesn't know what comes in and what goes out of the service, in this case the pizza, right? So this is different because in the case of ZK, you're actually not computing on the encrypted data itself. What you're doing is you're proving that you did a computation correctly without revealing the data you did it on. But you don't have this ability to actually perform computation itself. You don't have composability. This is where FHE comes in. FHE, the data itself is encrypted, right? So in the case of a blockchain, data is on a blockchain, and you're computing on it directly as you would on any kind of regular piece of data. So they're fundamentally different technologies. And I think ZK is very good when it comes to verifying and proving computation. But FHE is the actual solution when you need confidentiality of the data you're computing on.
Right. I looked a little bit at the documentation, especially in the context of artificial intelligence, given we live in 2024, and that's the only thing people talk about. Also, first of all, the amount of work that has been done is astonishing, right? So I see that it's you can have you have pandas interface, you can compile a PyTorch model. So effectively, that is. I didn't dig too deeply, but it seems like for most of the use cases I can think of, there's already an integration in place.
I mean, when we started Zama 4 years ago, there were three main issues with FHE. First, it was very slow, so you couldn't really do anything in practical time. The second problem is you could only apply it to very simple applications like adding numbers or multiplying numbers. You couldn't do machine learning, you couldn't do smart contracts and things like that. And third, it was extremely difficult to actually use. Unless you had a PhD in cryptography, good luck trying to make it work. So the first thing we did at Zama was actually build a technology that could apply to any kind of use case. So this is what we did with a technology called TFHE. So we're no longer limited in terms of what we can do. Then we thought, well, we want this to be easy to use for people. So we put a lot of focus on integrating this technology into existing developer workflows. So in the case of machine learning, that means integrating with NumPy, PyTorch, Pandas, and all of these things you already use. So you just write PyTorch Python code, and we convert it to FHE. And in the case of blockchain, that means basically writing Solidity code for a smart contract, and we hide away all the complexity of FHE. So it's really important, right? Because if you think about developer adoption, as a developer, you shouldn't have to learn like cryptography to start using these things, right? And this is what we're really striving for, making sure developers never worry about cryptography.
And so you mentioned that it used to be very slow. So how fast is it today? Right. So like if I compare, native speed versus FHE.
Well, it gets faster than Moore's law, actually. So in 4 years, we've made the technology about 100 times faster. So 100 times is enough to get blockchain type of use cases, right? It's enough to get small type of machine learning models. If you want to do decision trees, if you want to do, linear models, things like that. It's not yet fast enough for large language models. To get there, we're going to need some dedicated hardware acceleration. So ASICs for FHE. So the same way that AI is scaled with GPUs, FHE will scale with its own kind of chip. But once you have that, there is no reason why you wouldn't be able to do LLMs in FHE.
Fascinating.
So yeah, basically performance-wise, the bottom line is blockchain solved. Machine learning from 10 years ago solved. Machine learning of 2024, still working on that.
And so in the documentation, I see that today, if you compile a PyTorch model, you quantize it, right, to make it more.
Yeah, you have to. So FHE works over integers. So it doesn't have a concept of floating point number. So technically, that's not true. We invented a way to do floats in FHE, but it's so inefficient that honestly, you might as well just quantize everything and do everything in fixed points.
Yeah, makes sense.
I mean, think about it, right? Floats versus integer on a regular computer is much slower. So in FHE as well, right? It's the same problem.
Right. So in your, I guess in AI, so in blockchain, I think it's okay, let's do AI first, right? So in AI, one thing that we talk a lot about is private inference, right? So even if the model is open source, let's say Llama is open source, but I don't have resources to run 70B on my machine, right? What I would want to do is I would want someone else to host it, fireworks together, hyperbolic, and then I want to send them my data, but I want it to be encrypted. So how far are we from FHE being usable?
So it depends what kind of latency, right? If you need 1,000 tokens per second, as I mentioned, we're going to need ASICs to get there, clearly, right? But if you don't care as much about, I would say, latency, it works. So to be clear, you can run a Llama model in FHE. It's just that it's going to be so slow that it's probably not going to be very practical yet. One way that you could already make it faster today is to do what we call a hybrid execution, where some of the layers are done on the client side in the clear, and then the rest of the layers are done in FHE remotely. Because when you think about a language model, there are really only a few pieces which are very expensive to compute. In the case of FHE, what's expensive is the big matrix multiplication, the attention head, basically. That's very expensive to do in FHE, but everything else is pretty easy. So you could very well imagine just doing some of those pieces on your laptop or your smartphone, which would be very cheap, actually, because you're not doing everything, just some pieces, and everything else in FHE. And that could actually go pretty fast.
I see. Then another somewhat unrelated question is, I remember back in the day when ZK was getting popular, right? Some people were criticizing it for the cryptography was making assumptions that are more less strong than the assumptions we use, for example, in ED25519 cryptography. So, what are the assumptions of FHE? Is it is it the same? Is it only the set of assumptions we have in
So FHE, the standard assumption is that you want at least 128 bits of security. And FHE uses lattice cryptography. And so it's basically quantum, it's quantum resistant as far as we know what is quantum resistant, to be clear, right? But it uses the same underlying mathematical problems as what has been standardized by NIST for post-quantum crypto. So if you can break FHE, technically you're breaking the NIST post-quantum standard. And if that happens, I think we have a lot of problems. It basically means we have no crypto for quantum computers. And, well, I'm hoping that's not going to be the case. So it's as good as it gets in cryptography today.
I see. Okay, so that's more or less standard discrete log and whatever the assumptions I see.
Yeah. It's And the good thing also about FHE, which is important, is you don't have any side channel attacks, because everything that's happening on the server during the FHE computation only uses public material. There is no private key on the server. And because there's no private key on the server, there is no way for the server to attack anything unless they're breaking cryptography itself, which is great. And that's one difference, for example, with the hardware enclaves. Some people talk about using TEs like SGX for privacy. The problem with SGX is if I'm a malicious validator on the network, malicious node, I can actually measure the electrical current of the chip and reverse engineer the data that's going in it. So, FHE doesn't have that kind of problem. And so if you look at blockchain, if you're working on a decentralized network, you cannot trust the people running the computation, right? By definition, they could be anyone. And that's why you really need something that's cryptography secure and not relying on an honesty assumption from the nodes.
So I guess with SGX, I don't know that well how people execute those side channel attacks, but I presume you can write your code in such a way that it will, try to emit the same amount of electrical current, right? The bigger problem is that you have to trust Intel, right? So hey, it's a fully decentralized solution where, as long as Intel is honest, we're all happy corgis, right? So that's, I think, is a way bigger problem.
No, you're right. You're right. You could always try to write constant time code, but first of all, if you do that, you're going to realize that everything becomes horribly inefficient, right? Yeah. But also importantly, it still doesn't prevent you from putting an actual probe. So you have two types of side channels, right? In Ts, you have side channels where you're looking at cache access patterns. So in that case, you're correct, right? Like if the cache access is basically constant all the time and is always the same thing, then technically you cannot learn anything from it. But you also have physical side channels where you're literally putting like an electrical probe on the CPU to look at the bits coming in and out. And what's important to understand is that in the enclave, the data is not actually encrypted during the computation. What's encrypted is the access, right? So if you can put a probe where the data is being computed, technically you can read whatever is happening, and then it doesn't matter if it's constant time or not, right? You're just literally reading the content itself.
With FHE,
go ahead.
Okay, sure. So with FHE, right? Let's say that my code is not constant time code, right? It has a loop somewhere, right? So I presume in FHE you have to unroll it, right? Because if I don't unroll it, then I can measure time.
Correct.
Right. I see. So
yes. Correct.
Okay.
So FHE, basically, there is no branching in FHE. So effectively, FHE is constant time coding, right? Because you have to evaluate every possibility. If there were branching, you would be able, as you said, to measure time and basically learn where you are in the branch. But what we do have in FHE is the ability to do a homomorphic multiplexer. So you can have an encrypted condition that allows you to select one of multiple values, right? So you can say, if this encrypted bit is 0, give me value 1, otherwise give me value 2. So you can recreate branching logic, but in practice, you'll actually be doing both branches. So timing-wise, you're not going to learn anything.
Right. But like if so presumably I can do the same with SGX, right? Like I can have a compiler that will unroll all the loops for me. So that will solve it will not solve the probe issue, of course, where
No, and some people are trying to use something like ORAM, right, to make SGX more secure. But again, this assumes you don't have physical access to the server, right? But in blockchain, you cannot guarantee that unless you create like a permission network where you're forcing the node to run in a specific data center, where there is like someone with a gun in front of the door, right? There is no way for you to know whether someone has done that in their house or lab or whatever or not. That's a problem. Like you cannot have at the same time full permissionless open access networks and hope that people are not going to be malicious. Like blockchain,
right.
man, to be honest, blockchain is the most adversarial environment you could ever build anything for. Everybody's trying to break everything. The user is trying to steal money. The developer is trying to steal money. The nodes are trying to steal money. Like everybody's trying to break the protocol. So that's why you need like the most secure advanced form of cryptography. Like you cannot make any shortcuts in security in blockchain.
Right. So to that extent, so let's say, so the compiler that you have, right? Compilers. What is the target? I saw that uses LLVM. So presumably compiles into like into a native binary, right? So how do can I compile it into, for example, WASM or EVM to run it on chain, or do I need a custom runtime?
So to explain the stack that we have, at the low level, we have a library called TF-HERS, which is written in Rust and implements all the cryptographic primitives. This library can support CPU, GPU, FPGA acceleration. So you can decide what kind of hardware you want as a backend. And on top of this FHE library, we have a compiler that can convert Python code into effectively TF-HERS operations, which are then converted into a binary that whatever you want. And on top of that, we also created what we call the FHEVM, which implements FHE in the EVM so that you can use FHE in smart contracts. So from the developer perspective, it doesn't really matter which branch you're going through, whether it's the compiler or the FHEVM branch. Both of them are actually resolving to the same cryptographic library. And that cryptographic library is just Rust, right? So supposedly, I assume you could export that to WASM or to, we even have C bindings if you want to use that, for example. That is like whatever works with LLVM and technically should work. We just don't necessarily have like the tool chain to automate it, but it should work.
Right. And so let's walk through a couple of use cases, right? So let's say on the blockchain, right? So let's begin with a simple case. Would it be possible to implement something like Tornado Cash? Setting aside whether someone would go to jail for doing so, right?
FHE is Turing complete. So technically, you could do whatever you want. In practice, the privacy and confidentiality model of FHE is very different from mixers like Tornado Cash. Think about it this way. In the case of Tornado Cash, the transaction data and the state that comes in and out are public. So you can see how much goes in, you can see how much is in the mixer, you can see how much goes out. What it gives you,
Zcash, right? Like in Zcash, even the amounts are hidden.
Yeah, correct. But this is not a composable protocol, right? Like it's a very specific protocol. But in the case of Tornado Cash, what you're hiding is actually the trace of the transaction. So it helps you anonymize who's been sending money. This is kind of like using Tor to access content online. The website content is public, but you're basically using a mixer to access content via Tor, which anonymizes your IP address. This is what Tornado Cash does. FHE is more like Signal. The actual transaction is public, so you can see that Rand sent money to Alex, But what is encrypted is the amount and balances. So this is like a messaging app. Your telecom operator knows that I sent a message to your number, but they don't know the content of the message. And that's really what FHE is for, is hiding the actual data, not the trace of the transaction.
But the question is, well, I guess, like the question was, would it be possible to use FHE to even hide the recipient and the sender, right? Like if the state, if we imagine that the state, because FHE works on the encrypted data, right? Like consider the map from user accounts to balances. If that data is also encrypted, right? They send a transaction that says, like the transaction it says send money from Alex, send one Zama token from Alex to Rand, but all of that is encrypted, and the state is encrypted. Like in theory, that would work, right?
Yeah, I mean, in theory, you could do whatever you want. In practice, you probably don't want to use FHE for that because, as we said earlier, FHE doesn't have branching. So doing a lookup of an encrypted address means scanning the entire address list, right? And doing a homomorphic comparison on each to determine which one. Basically, you have to scan a whole database. So if you want to do that, it's much better to use ZK in combination with FHE, or to use something like stealth addresses, right? I think if I was to implement privacy with regards to the recipient, I would actually use stealth addresses, which I think solves the problem more than I would use like an encrypted key value store, just in terms of like performance, right? So yeah, possible, but probably not how you would want to implement it in practice.
So then, if not private transactions, what are the like biggest use cases you see?
No, so confidential transactions is a big use case, but the use case here is hiding the amount and the balances, right? I would argue that Venmo. If you look at Venmo, actually, Venmo, you can see who sent money to who. You just don't see how much, right? FHE gives you that on chain, right? Effectively. That's one use case. Another big use case is confidential swaps, of course, right? So you can hide the amount you're swapping. I guess you could also hide a token you want to swap, but the amount is easier. If you do that, no MEV, no front running, anything like that. So I think you can make it would be the equivalent of like of trading on a dark pool, right? It would be something like that, which would be quite nice to have on chain. Another big use case I'm personally very fond of is identity. Because if you think about it, today, there's no way for you to have your identity on chain and make it composable, right? You can make ZK statements about your identity, but you don't have like an identity object in a smart contract that you can use as part of like a DeFi compliance flow, for example. But with FHE, you could have some KYC provider encrypt your identity, your age, nationality, put that on chain for you. And then whenever you want to use like a compliant DeFi product, that product could automatically on chain request to verify some condition. Maybe you're not American, right? Or something like that. The beautiful thing is, because everything is encrypted, from the outside, the transaction would still go through, but in practice, nothing would happen in the encrypted state, right? It would basically just reject it behind the scenes. Okay. So if you have identity, you can build compliance into DeFi, which, whether you like it or not, is what we need to onboard 1 billion people on chain. But you can also start building governance systems, because if your identity is encrypted, oh, and by the way, with FHE, you can also do encrypted votes on chain where people don't know what you're voting for, right? If you have your encrypted identity and the ability to do encrypted votes, you can do encrypted governance, right? If you do encrypted governance and you've got encrypted currency and encrypted identity, it's starting to look like a country, right? So you could even take that even further. You could imagine running all of a country's services on chain without anybody knowing you're the one accessing them, right? Like that's huge. Like we can create like a state OS with FHE that runs fully on chain.
But in your example, right? So you mentioned an example. So let's say that the whole KYC information only says whether I'm American or not, right? So it's a 1-bit information. Like I go to Fractal is like it's a KYC provider, right? And there's a smart contract, and they say, hey, Alex is well, in my case, I am American now, right? So it says, hey, Alex is an American, right? And it's encrypted, right? But then if there's an endpoint that can return you whether I'm American or not, then obviously you can immediately deduce the information, right?
So what you would get is an encrypted bit, right? So whenever the DeFi protocol, let's say you want to make a swap, but to make the swap, the protocol wants to make sure you're not American. It actually doesn't have the ability to decrypt your identity. What it does is the smart contract would basically call your identity on chain and basically say, hey, is that person American? What they would get back as a result is an encrypted bit that says yes or no. That encrypted bit can then be used to effectively nullify the effect of your DeFi transaction, right? So it's like a no-op. So from the outside, the transaction is not actually reverted. The actual transaction happened, but it had no effect on the state. But nobody knows. Right? You know as a user.
No, it fizzled. Yep.
Exactly. Right. See, that's what's so powerful. It's like it's completely oblivious to the outside.
Yeah. I guess it still needs to change something, right? Because we would see if state didn't change at all.
Oh, it changes the ciphertext, but you don't actually know what the value is, right? So for example, if I send you, imagine I want to send you some tokens, but I don't have enough balance. What you would do in FHE is you would check in FHE that your encrypted balance is bigger than the encrypted amount you want to send. And what you get as a result of this encrypted comparison is an encrypted 0 or 1, right? Yes, you have enough funds or you don't. You then multiply this encrypted bit by you multiply the amount by this encrypted 0 or 1. If you have enough, the amount stays the amount. If you don't have enough, the amount becomes 0. And then you actually add and subtract in FHE this normalized amount. So in practice, the balances, the actual bytes of the ciphertext of the encrypted balances changes, even though the value contained in it didn't. Right? So from the outside, you can see the state has changed, but you don't know the value inside of it.
But why does it change if it's subtracted 0, right?
Because every encryption of 0 is different, right? You can encrypt 0 20 times. Every encryption of 0 will be different. You never have twice the same value for an encrypted value.
Okay. So it's not like a bijection from an encrypted value to
No. Basically, the way it works, the encryption is you take your value and then you add some random noise, right? And then on top of that, you're basically adding like a mask, right? So as long as the noise is different, which it should be if you encrypt it correctly, the noise is always going to be different, then it's impossible for you to tell without breaking, well, the cryptography.
Yeah, well, I guess that's a very important point here, right? That two identical states will not have the same encrypted, encrypted view. So that's so you cannot tell if something didn't change by looking, at the encrypted. That's a fun. So I guess the long-term vision of a whole governance on chain is definitely something very exciting, right? But
I mean, look, I'm originally from Lebanon, right? My parents were from Lebanon, so I can see my origin country basically starting from scratch soon, right? Like, once everything is gone, we're gonna have to rebuild everything. If you think about it today, if you want to build a state which is efficient and transparent, you still want confidentiality because, I don't want my neighbor to know what I'm voting for, how much money I have, right? That's private information. Then doing it on chain is a good idea. I'm convinced that you can cut the government spending by 80% if you use a blockchain because you don't have any middlemen. You still need people for edge cases and whatever, but most of the things that people do could be automated. And FHE is the confidentiality piece that makes it possible to even consider that. So we're still far from that, but let's start with running a company on chain with FHE, then maybe running a city, then maybe running a region, then a country. And then what happens when countries are all on chain and become composable between them? Like, try to think about this idea of like composable politics and composable governments. I mean, there's an infinite number of things that you can do from that.
Yep. We can have like a European Union on chain. Okay, cool.
That would be a good thing. France right now, I'm in France. France right now is going through a major crisis of government spending. So believe me, right? Like, it's on everybody's mind. We have to do something. And I think blockchain with FHE is the way to get there.
Yeah. Okay, so we're almost at the time. I guess I would like to close with the question of what do you think will be the biggest and coolest use cases that will emerge in the next, a year or two, right? So like before we get into the full adoption by the whole world, what are the biggest things that will happen?
I think we're going to start with DeFi. That's simple. It's one of the biggest use cases in blockchain. Let's start where the use case is. I love machine learning. My background is machine learning. I built a privacy machine learning company. So obviously I want machine learning to get there, but being realistic, blockchain is easier to do with FHE than machine learning today. So I think that's where it's going to be adopted first.
Okay. Yeah. Sounds exciting. Okay. Thanks a lot for joining us today. Thanks,
Alex. Thanks for
sharing the wisdom. Okay.
Have a good one.